Raspberry Pi 5 hasn't just been a hardware effort. We always say every hardware company is a software company. We probably have two software engineers working on all of these things for every hardware engineer. It's kind of, I guess it's an evolution, right, of the Pi 4. It's an evolution of the previous Pi platforms, particularly the Pi 4 platform. Perhaps we could talk a little bit about the evolution of the Pi 4 software environment from launch, because we grew a lot of features over the course of the Pi 4 program, right?
So when we did the Pi 4 launch, we kind of used the Pi 3 software as a baseline, but between then and Pi 5, we've been pushing lots of software out of the VPU firmware and into Linux. So the biggest example of that is probably the display driver, the KMS driver stack. So Pi 4 has, I think, at least 3 display driver implementations there.
Yeah,
So,
it's got classic, so Discman X. It's got fake KMS,
yes,
firmware, FKMS, which is either firmware or fake, depending on your view, and then real KMS.
Yeah.
Which we call full KMS, which I always get confused with FKMS. I'm like, no,
That's not helpful.
KMS.
So for Pi 5, we think, well, KMS was pretty mature, so we decided, okay, let's just have that as the display driver. It's a little bit of a challenge whilst bringing up the chip because we didn't have the driver. So how do you verify a chip without a driver? So you end up writing test things and evolving that. So we kind of had very cut down display drivers to verify the hardware whilst we were simultaneously bringing up the real software thing. Similar, the ISP. So the ISP, for various historical reasons, had to all run on the video core. Pi 5, full Linux.
And that was ejected. That's been ejected.
It's ejected
over the course of the Pi 4 of Pi 4's lifetime. We
We
slowly ejected it.
So there's like a bit on Pi 4 which is still in the firmware, which is actually, if you like, programming the ISP. But there's then like the rest of libcamera talks a consistent interface across there, and that was like this has been planned. Like we say, it's like, since Pi 4, actually we've planned this like from quite a long time ago, starting with like Pi 1-ish, 2-ish, when we start with the GPU stuff. Like we wanted to start to make an open source GPU so that we can do all of our GPU stuff from the ARM,
and it's this gradual whittling away of the much loathed blob. People talk about start.elf, the firmware that runs on the VPU, which in 2012 ran almost everything in the system. It ran HDMI, would negotiate with HDMI for you, and it would render your triangles for you, and decode your video, and process your camera images. And things have gradually been carved away from this. To the point so I guess in Pi 4 you're kind of in this sort of liminal kind of space where GPU's gone, so 3D is gone. That's Mesa. Display scan out and ISP kind of have gone over the course of the Pi 4 generation. Encode is still in start.elf, and then Pi 5 we've turfed out. All of those things, including, of course, encode, because there is no encode hardware on the platform.
Yeah. Pi 4 had H.264 decode, not on Pi 5, and HEVC was already on, was always been on the ARM for Pi 4. So that gets us to an interesting point where actually all of the multimedia stuff is now running on the ARM. So for Pi 5, why do we need start.elf? And we came to the conclusion we don't need it. So we still have some firmware, but that firmware is essentially just power, clocks, DDR and it. It's pretty much as small as we can make it, so it's completely self-contained.
And all of that does all of that live in the SPI flash on the board?
The SPI flash has everything that it needs to load the Linux kernel.
So no remaining if you run on a Pi 5, no remaining stuff in the SD card, in the SD card file system. Yeah, super cool. Right, we made it. It only took us 11 years and 6.
Winding out.
11 years and 7 hardware generations, but we got there in the end.
Yeah, the other interesting thing I think, where one of the things I really pushed for when we first started doing with Project Y is making sure that when we test Project Y, what we do is actually write Linux drivers, because what our tendency is is like whilst you're testing silicon, what you do is you just like, somebody writes like a really simple driver, it just, punches some registers, checks some things, does some stuff. And of course, what you end up with then is you get your chip back and you check and you go, yeah, it still works. And they're like, great, how do I run this on Linux? So, oh no, you now need to write 1,000 lines of code. And you're like, oh, right. So doing that meant that as soon as we got it back, we were actually able to run code and
do all up tests.
Yeah, absolutely.
So on the multimedia side, multimedia has largely migrated from being the responsibility of the VPU, the responsibility of the blob, to being the responsibility of the ARMs, the big ARMs on the application processor through a variety of standard interfaces, KMS, Mesa, libcamera, free for L2.
Yep.
For HEVC decode?
For HEVC decode, yes.
Yeah,
V4L2, stateless.
Yeah.
Stateless. Yep, that's right.
So these are all Linux standard. These are all Linux standards. So that's very standards based. As you said, the other big change in the platform is that all of the interfacing. So multimedia has gone one way. All the interfacing has kind of gone in another direction, right? In that it's gone off the core chip onto RP1.
Yeah. So, and that, that's really good because it means that our drivers become completely standard, and i.e. they, a lot of our drivers are standard anyway because they use standard interfaces, they use standard like modules, right? So your USB and your SDIO and that kind of stuff, they're using standard drivers with some maybe little modifications here and there, but the great thing is that you set up that PCI connection, and then all your devices there on the other side, you have a driver in it, and it just talks to those as if they are on the same chip, but obviously they're not. It talks down a PCI link, so that changes some things, but also makes it much easier. And it also means, of course, you can use that wherever you want, and we can use Project Y standalone if we wanted to. Not that we would, but actually you can plug it into any of them.
RP1 now.
Oh, RP1.
We've launched a chip. It's got a name.
Yeah, it's got it. It's a chip. It's RP1. Yes. Okay. Yeah. Project is fair enough.
And in fact, when we were developing those drivers, we even had PCs, because we had PCs.
Yes.
We had a few development platforms. We had PCs connected to the FPGA prototyping platform.
Yeah.
I think we had PCs with actual RP1 silicon.
Yes, that's right. We got that card that you can plug into the PC. Yeah.
We had 2711. We had CM4 with. For a more ARM-like environment, I think we have CM4 connected to the...
And with the PC, it was like, the drivers are slightly more difficult because they don't have, x86 doesn't have device tree. So it's slightly different in terms of configuration and that kind of stuff. So it's actually, it's not as, people kind of like, well, could you do that? Can you make an x86 Raspberry Pi? It's like, oh God, that would be a lot. It would be a lot of work. You could, but it's...
you could put RP1 down with an AMD APU or something, and you'd end up with a thing that felt, in interfacing land, felt very Raspberry Pi-like, but it wouldn't feel quite like a Raspberry Pi.
That's it. Yeah. So, but anyway, but that's actually really, really great because it does mean that we got this one bit that does then the kind of our interfacing, and it's all the drivers are there. We've tested them all in simulation with those drivers as well. So, we've had a couple of years now of those drivers, so it's been good.
And again, mostly standards-based interfaces. So USB is XHCI.
Yep.
Ethernet is the Cadence core, but there are other SOCs that have that. It's not standards-based, but there are other SOCs that have that core in, so we're able to use drivers for that core. I guess the MIPI stuff is rather more That's rather more custom. So the interface to the CSI and DSI is custom to us.
And that was just the great thing about that as well is just like how easy it seemed to be. I mean, I say easy. I'm sure if I spoke to someone like Nick and said how easy was that, I'm sure he wouldn't come. But everything just worked.
Everything seemed to. Bring up didn't seem to be that difficult. We were kind of waiting for the horrendous thing.
When's it going to get really hard? And it just didn't happen, and things just kind of worked.
I mean, there's a lot of it, but
how many times did you ask me, does DSI work? Has anybody checked DSI? And I'm like, no, they've tested it all.
And when we started to see these all-up tests, I guess in the springtime, when we started to see these all-up tests where you'd have a dual 4K P60 desktop, and a 1080p DPI monitor and a DSi display and a camera.
And a camera, yeah.
And hammering the network and hammering 2 USB 3 SSDs at the same time.
And you're like,
thinking,
that's
it's
looking
not
good.
falling over. It's a testament to the amount of all-up testing, to the amount of testing that went in, and in particular this kind of all-up testing that happened at the FPGA stage, right? That works really nice.
I mean, we've always said it's like testing at silicon level, trying to unit testing blocks is one thing, but actually because they interact in a system, and if you do not do that in simulation, that's where your problems are. They're always in those interactions. So trying to do as much as you can. You can't always, you're not going to be able to run Linux in a simulation, but trying to do as much as you can to kind of reproduce that scenario, and it does work. It's great. Yeah.
What about boot modes? Do we have the full set of boot modes at launch? We're several weeks away from. We're filming this. We're filming this in advance. So, do you believe we will have the full set of boot modes at launch?
Well, I'm not writing them all.
Oh, right. So yes, then.
So yes, definitely. Yes, no. SD boot works. Obviously, we've been using that for ages. USB. That was fun. We have 2 XXGI controllers and RP1. That makes boot enumerating USB devices slightly more entertaining. But yep, that works. I've been using that for over 6 months. NVMe, that just worked. It's the same code. The nice thing about a standards-based interface is that there's a little bit of plumbing to talk to RP1 from the VPU, which has slightly harder access to PCIe than the ARMs, but once we did that plumbing, the existing code just worked. There's a little bit of work left to do for the Ethernet, but I think it's pretty close.
Yeah, and then anything. It's mostly just like getting packets across the Ethernet interface.
It's only the Ethernet MAC driver and testing it, obviously.
But all the rest of it's already done.
Most of the code. It's a big project. It was very complicated, so what we couldn't really afford to do is just go and do all these things in isolation and then do a big integration merge. So basically, we had to do everything on the main code line all the time, and try not to break stuff, and we've been reasonably successful because we haven't had an integration nightmare.
That's cool.
That's good.
Yeah. How many functions did the button have?
This is the most controversial
the most
element
complicated button. That's probably the most complicated bit for software, actually.
Yeah. How do you make a button do lots and lots of things?
If I can't play Tetris just by pressing the power button, then you've not done it right. Tetris in the bootloader.
I have been kicking, like every now and again I'd say to Tim, so the game that you could put into the boot ROM, it's like, no, we don't have the space for it.
We could at least have the little dinosaur that runs along and jumps over things.
That's what I said. Like, so literally, it's like, it's like like you said, and the first time it's like, you can't do it. Like, we haven't got time. It won't fit. Like the second time was kind of like, well, you could do it, but it's just like we haven't got the third time was kind of like, well, I might think about something. I don't know. I'm just not asking anymore. I'm just like, I'm assuming
it may appear one day.
Yeah.
There are many places.
There's a lot of other work to do.
There are many things we can do there. A big change actually for the bootloader was a new power supply. We have a very sophisticated power supply. We can do lots of stuff with that.
And we go out and we can interrogate. So we now have PD. We now have a PD PHY on the CC pins, so we can go and interrogate the power supply and say, are you a 5 amp?
Yes.
Are you a 5 amp power supply? And then we turn off. We have the quite an aggressive USB current limit by default, which you can turn off if you want. Yeah. But we have quite an aggressive USB current limit that we then turn up. Yeah. So that's a chunk more complexity in the system.
Yeah. It's going to be fun getting used to, but
also, I was going to say, the PMIC itself has built-in ADCs, so you can actually look at the core voltage and the core current, and you can use that to profile your usage. And we've just got a little video core gen command. So,
draw a graph.
We can draw graphs. We can look at benchmarks. You can look at the 3.3 voltage and current and see all of that stuff.
We should maybe talk a little bit about testing, actually, that, particularly the stress vectors, like finding the stress vectors always a challenge for us, right?
Well, because you never know. One of the problems is you never know, have you actually found the stress vector, right? Because that's what we've done in the past, right? Is like, thinking we found the correct stress test, and then finding that, like, we release it and then somebody finds something harder.
When we say the stress test, we mean the thing you run in production, right?
Yeah.
The thing you run in production test. Yeah.
Yes.
Yeah.
Which is LinPack again?
It is LinPack again, yes. Although we moved, it's a 64-bit LinPack. We've kind of, so that was, yeah.
Is it a neon LinPack or a scale LinPack?
There is some neon, but
Because
yeah.
you've got those, each CPU's now got 8. It's got 2 full-width neons, right? So it's got 8 FPUs in it, and so you can light up 32 FPUs constantly. That's kind of that's a lot of power. Yeah.
That's a lot of power, yeah. And actually trying to manage the code, so you don't want it to be stalled waiting for SD RAM. So you're trying to optimize your test set to fit in the caches, and then at some point, is this really realistic? So we just keep iterating on that and measuring it, and but I think we're pretty happy with that now.
Yeah, and that stress, because it's what tells us whether or not a device, to trim out variations in process that you get from silicon. Natural silicon has variations in process, and a lot of other companies will bin chips. They'll have fast ones and slow ones, and we don't do that. We try to make everything run at the same speed, so fast devices run.
This is AVS, adaptive voltage scaling.
Yeah.
It feels like the software environment's much more mature, right, than Pi 4 was.
Yeah, I mean, actually, so we kind of started with the port of the Pi 4 software, which had quite complicated AVS implementation, and then actually as the project matured, we started realizing actually we don't need to do all of this stuff. So there's kind of satisfying thing of deleting lots of this code at the end, and we've actually got fairly simple voltage.
Simple rules.
Yeah,
right?
it's simple.
Run
simple
fast
rules.
and then throttle back.
Yeah, and even at the kind of idle or maximum throttle thing, it's still dual 4 KP60 and probably getting on for twice as fast as a Pi 4.
It's kind of fun. And all this is coming along, so this product's also coming along with an interesting time for us in the software world, right, which is Bookworm. Debian, how many?
Sorry? Oh,
number
12?
12?
Yeah.
Bookworm. Debian Bookworm.
Yeah. So that's, I think, we wanted to get, obviously one of the things that we wanted to do is to have Pi 5, we kind of like wanted to start there. We kind of like, so that's where we've been, is kind of like trying to make sure that Bookworm and Pi 5 kind of come out, are there together. That's the thing. We weren't going to use Bullseye. I didn't want to kind of like port Bullseye and make that work.
Because Bullseye is very old now, right? It's 2 years since Freeze, and so in practice 3 or 4 years since packages started to be selected, right?
But also, one of the things, great things that happens with Bookworm is that a lot of stuff has changed in such a way that it allows us, number one, to use more recent Mesa versions, right? Which then allows us to then use much more recently released implementations of Compositor. So previously, when we went into Bullseye, we said what we did is we changed our Compositor. We were using XCompman that we were using for doing that, and then we changed that to Mutter. Now it's changed a lot of stuff. Now it was kind of like and the idea is that we were trying to get.
So when you say compositor, you mean the thing that assembles the screen, that puts the windows together to make a desktop.
Puts the graphics, draws the 2D graphics and puts it into a single window to then display onto that screen. Separately from the compositor is also a window manager. That's the thing that actually handles the fact where there are many windows.
Are you really going to try and describe the difference between compositors and window
Well, no, what I was just going to say is that the difference, like Mutter is both of those things. So Mutter actually contains, is like one thing that contains all of those. And because it contains all of those things, they've made choices that weren't quite our choices. Like if you like, there were things that they'd made which they're not perfect for us. But it would give us it's like a pathway that we could see to get from a completely X Windows display manager through to Wayland, where Wayland is, if you like, the future. That's where people have been, we've been working for a very long time to get a window manager which is more secure, but also has the ability to use more of the hardware, especially on a Raspberry Pi. We've had special hardware on Raspberry Pi ever since Raspberry Pi 1 that can actually do most of that composition work in hardware, and that would allow you to accelerate it much more. So I've always wanted to be able to do that, to use that hardware, but there are many, many complexities. The idea is that
and too many complexities in X world, right?
Sorry?
In legacy world, in X.
Yeah.
Too many complexities.
Just yes.
To ever really fight.
To ever do it, because they're like so intertwined. There's so much in like with all your multimedia systems, and everything from the format of the pixels all the way through to getting it through a GPU onto a screen, into a screen, like that all that stuff is much more complex. Because they're then separated, because at least what we've done is we've chosen a new window manager called Wayfire. And because that's separated, really the window management part and the composition part kind of quite considerably separated. It allows us to kind of look at the composition on its own. It's much simpler. Allows us to kind of understand it ourselves and then to insert and change it in such a way that we can use that hardware. And that's what we're trying to do, is use the hardware that we have available on Raspberry Pi and always have to do that acceleration, that hardware acceleration task. And for example, what I would like to be able to do one day is to be able to play a HDR video, and then see that on the screen and integrate it into a full window. So you can have a window on your screen that has HDR video, whilst the rest of your GUI looks completely normal, not all with different colors and things. And that is what the hardware should be able to do.
For the first time, we're not there, but we're within reach of it.
We're in reach.
Do we have benefits from it already, though?
Oh, absolutely. Yeah, it makes the difference. The difference is
on a Pi 4.
Well, on anything. I mean, yeah. So yeah, any of the definitely makes a big difference. But we have a lot further to go. But yes, already it looks. And
with Pi 5, you're stacking together two things. You're stacking together hardware, which is 2 to 3 times faster, with a display subsystem, which gives you a path to memory, which is twice as fast. Sorry, a path to pixels to the screen, which is roughly twice as fast. So you're kind of seeing all of this is arriving at the same time.
Yeah, absolutely. So yeah, and then, I'm really kind of I really want to see not just Pi 5 being awesome. I also want to see improvements in Pi 1, because that's what I'm expecting, is to get there to the point where Pi 1 suddenly, you're playing full screen video at 1080p, and that's what you should be
Which
able to
you can do in a Disman-X layer using the classic scan out. You can absolutely play Big Buck Bunny as a sort of a detached full screen overlay over the rest of everything on a Pi 1 at 1080p. The question is, why can't I do that in VLC?
Yes, yeah, absolutely, and that's always been difficult. It's always been hard to get those pixels onto the screen.
If you touch the pixels, you die, is the rule.
Yeah, exactly.
And even on the new modern fast devices at 4K,
yeah,
if you touch the pixels, you die.
Yeah,
right. Even if you touch them with the GPU, you die.
Yep.
Or you're at risk of death.
It's very difficult to, because so much data, and yeah, processors are very good at doing it, but they are not as good as just pure hardware. It's so much faster. So that's kind of that, trying to get that in place. So that's what we've been working on significantly. It has a lot of changes. There are a lot of differences, much as there were in previous releases. It's got a whole bunch more differences, but we think actually it's looking pretty good. We ran a beta test of the software, so that actually we have a lot of people having a little play, so we get more feedback than we have done in previous years. So yeah, but that's looking really good. Yeah.
Excellent. Does feel like a desktop computer when you sit in front of it, right?
It was surprising how fast Dual 4K P60 was. Because even when we were doing the hardware bring up, it's like, is it really going to be usable? When we put Wayland on at the same time, then it's like I'm dragging windows across screens. Like, yeah, this shouldn't be this fast.
My MacBook struggles. My MacBook struggles. When I plug it into a 4K television, it chugs, right? And it's a fairly recent piece of hardware. It's remarkable how well this works with two 4K displays.
Absolutely. My laptop, side by side. Facebook or YouTube or whatever on there, so it's pretty kind of JavaScript heavy website. I can't really tell the difference between that and my PC. It is really good. Yeah. Not that computers are only meant to be doing browsers, but let's be honest, that's kind of what most
It's a really
of them do.
important use case.
Yeah. But yeah.